Okay. So the last section that we have to go over for the rest of the semester, most of the rest of the semester, is Carbonyl Chemistry. And I haven't updated the folder for today with the reading assignment, but it's going to be whatever the next chapter is. 25 seems close. But I'll update it today. So here's what we need to know sort of as a setup for the next two chapters. Because the next two chapters on carbonyl chemistry, and carbonyl chemistry is probably the most important part of organic. It's unfortunate that it always comes at the end, but that's the way they write books, so it's not like I can move it to the beginning. Unless I want to write my own book, which not today. So, in terms of the carbonyl chemistry, we're going to, first of all, group aldehydes and ketones together. So, that's the first grouping we're going to make, and that's what we're going to talk about. But I'll introduce the other carbonyl functional groups that we're going to be talking about in the next set of chapters. So those are called carboxylic acids and their derivatives. So we have a carboxylic acid, and then we have their derivatives, which I'm going to show you in a specific order that we'll get into a little bit later. But first of all, we have carboxylic acid chlorides. We have the carboxylic acid anhydrides. We have esters. And we have amides. So amide, ester, anhydride, and acid chloride. Some of these we've done reactions with in the past. We've done reactions with acid chlorides. We know how to make esters from carboxylic acids. We know how to make amides from carboxylic acid chlorides and amines. There's also one that doesn't quite fit this mold, and that's nitriles. So when we get to this, we'll see why we group these together. We'll also see why we're separating these two sets of carbonyl compounds right now. So if you look at these two columns that I've given you, the difference is all of them, I assume, have one R group attached. And so the question of what's the other group on the other side of the carbonyl? And for here, it's an alkyl group and a hydrogen for aldehydes and ketones. For all of these other groups, it's OH or Cl or a carboxylate, an alcohol, an amine. And the reason that we're going to break these up into these two sets of columns is I'm going to generalize the structure of carbonyls to look like this. There's a Y group attached. And the question is, can that Y group leave? Here, with R and H, or with a carbon and a hydrogen, it's not leaving. Right? Those are our groups that never act as leaving groups because they are the strongest bases that we have. So these groups, these are not going to be a leaving group. On the other hand, on the other side, all of these, they could be a leaving group. And actually, for the derivatives, I've ordered them from chloride down to amide in their ability to be good leaving groups. So Cl is the best leaving group, and the nitrogen is the weakest leaving group. And again, leaving group ability is based on what? One thing. It's basicity, and it's an inverse relationship. So that's why we're going to divide this into two sections, is because my ultimate goal here is going to be to add a nucleophile to a carbonyl. And the question is, can the Y group leave? So here's what we're going to do. And we've already done this, actually. I'm going to add a nucleophile to this. Let's just say, for the sake of argument, let's start with a negatively charged nucleophile. That negative charge comes in, moves that pair of electrons up to the carbonyl, oxygen, and I end up with that, generically. What's this molecule going to try and do? Reform the double bonds, so this pair of electrons is going to come down here. It can only do that if what happens? Something leaves. So our group going to leave? No. Is the nucleophile going to leave? Depends. Depends on what the nucleophile is. So what does this remind you of? We've added negative charges, what? Grignards. So if the nucleophile is equal to a C minus, we have a Grignard. What other minus have we added to this? C minus. What? H minus. So we've had C minus and H minus, and this was something like sodium borohydride or lithium aluminum hydride. So we've done these reactions with this molecule. And we've done it with different Y groups. Okay. I feel like I need to refresh people's memories. Or maybe it's just review and everybody's bored. I'll take the refresh memory route. So think about if I had an aldehyde or a ketone, and I added to it like CH3 minus. What happens in this case? So if I had originally an aldehyde or ketone, an aldehyde or a ketone, and I added a Grignard to that, I would get a molecule that looks like this, sort of. What happens? Oxygen tries to bring the pair of electrons down, and what? Can't. Because there's nothing there that can leave. H and carbon cannot leave. They're too strong a bases. So then this molecule gets stuck, and then what happens? It just waits around for the H plus to be added. But we did do a Grignard reactions where we took something like 2 equivalents of, this would be methyl Grignard, and we added this to a carboxylic acid chloride or an ester. And what happened there? CH3 comes in, adds to the carbonyl. We ended up with an O minus. System tries to bring back down, tries to bring the pair of electrons back down to form a double bond. Can it? Yes. Because what's going to leave? The chloride's going to leave. And if this was an ester, if this would have started out as an ester, we would have an OR group here. And when this pair of electrons came back down, that OR minus would leave. Not necessarily as fast, but it could leave. Our only prohibition on something being a leaving group is no H, no alkyl group. Everything else could leave. Josh?
And is that second one when we have an ester trying to get that OR group to leave, is that basically only based on heat?
It is initially. It is because we're going to heat this system to make it go. So, yes, although what happens here is that once either one of these two happens, we end up with what? We end up with a ketone. We end up with a ketone. And then what happens? The second equivalent of CH3 minus comes in and adds to the ketone. So the critical part here would be, let's say this only occurs like one every, I don't know, you'd say every million molecules. But once it happens the first time, that molecule's gone. When it happens the second time, that molecule's gone to the final product. So eventually everything will be moved over to the tertiary alcohol. So we've actually seen Y be a leaving group. We've also seen Y be a non-leaving group in the past. And I introduced those mechanisms to kind of prepare you for now, although I should know not to do it so early. But if you go back, you'll see they're there when we talked about Grignards. And so that's why we're breaking these two sets of molecules up. Because if this group can never leave, I can never substitute the nucleophile for that group. If Y leaves, then I can substitute that group and get a substitution reaction. It's called acyl substitution because it happens at a carbonyl. Okay. So we've seen this before, and that's how we're going to break the molecules up. So let's start with aldehydes and ketones. And I'm going to write my generic, I'm just going to start with an aldehyde. Although if you wanted to write the mechanism for every one of these reactions as a ketone, you just go through and erase the hydrogen and put an alkyl group in there. And while there won't be any practice problems or take-home quiz problems for you for Wednesday, there will on Wednesday for Friday. I'm just way behind, and it's only Monday. And I'm not even caught up from the last 2 months. So what are we going to do with this? We're going to add a non-carbon, non-hydrogen nucleophile, because those are Grignards and reductions. Already know how to do those. Let's add water. Now, the interesting thing here is I'm going to add a neutral nucleophile. So I'm not going to add hydroxide, I'm going to add water. Because something totally different happens when you add hydroxide to this. It actually it forms an enolate and it goes through condensation reactions. That we will do probably in the last 2 periods of the semester, because that's always last. And then there's always 20 questions on that on the ACS test. There's not really 20 questions, but people are enamored with this. They should teach the class and know that we only get to this at the end. So me babbling is not helping us get to the point. So I'm going to add a neutral nucleophile. Now if I'm going to add water, I'll add ROH. Same thing. All right, so neutral nucleophile reacting with a carbonyl. I would like this nucleophile to be able to come over and attack the carbonyl. The problem is both of these nucleophiles are weak. And if they're weak, they can't attack the carbonyl by themselves. So what I need to do is help out by adding an acid catalyst. Okay. So if I add an acid catalyst to this reaction, so I'm going to add water, aldehyde, acid catalyst. What's the first step in the mechanism? Protonate the oxygen. Right, you got to say that aggressively. I mean, it's not, I mean, it is kind of, I say it over and over again, but the method to the madness is that that's what you do. And so if you're looking at this going, oh, oxygen species, acid, protonate the oxygen, that's what you do. Right? So it protonates. Now, there's another resonance structure for this molecule. I could take this pair of electrons in a double bond, move it up to the oxygen. So the second resonance structure that I could get would have the plus charge on the carbon. Now, as you're looking at that, you're saying, oh, that second one's bad because it doesn't have a completed octet. Yeah, but it's not that bad. The resonance hybrid for this, the resonance hybrid would have a partial bond to the oxygen, partial delta positive charge on carbon and oxygen. So that would be our resonance hybrid. So, how did this help? How did the acid help out the carbonyl? Well, Josh.
Does it shift the positive charge to the carbon, and therefore it's more accessible for the weak nucleophile to attack?
Yes. The only thing I would add is I would say that it adds a positive charge to the molecule. And a good chunk of that positive charge is going to end up on the carbon. So what did I just do? I just made that carbon more electron poor. And so the poorer it is, at some point, you know, if you're giving to a poor enough species, you're rich. So while we think that these are basically weak, if the electrophile is really poor, it'll still add. So by protonating this, we're now going to have the water add. And it can add to either one of these two resonance structures. I'm going to show you both. You know, pick one. So the O- could come and add to that carbon. If it did, then the pair of electrons would go up to the oxygen. So that I would end up with an OH group, and then the entire water molecule adds, so we're back to like our beginning days of SN1, and I get that oxonium ion. What? And so then this pair of electrons, if it just adds to the carbocation, I end up with the same thing. So you can choose whichever one of these resonance structures you want to add the water to, but you're going to end up with the same molecule. So now what's going to happen? I'm going to lose a proton because this would be like to become neutral. And so if I lose my H+, I now have my final product. And this molecule is called a hydrate. Now here's something kind of new. So the acid is a catalyst, so it's still hanging around. What could it do? It could protonate one of the OHs, and we could go backwards. And then what could happen to this molecule? I could lose water and end up back here. And then what can happen to that molecule? It can lose H plus and end up back here. So we're going to be talking about reactions with equilibria. So if you add water to an aldehyde or a ketone, so this could be H or it could be R, you're going to end up with a hydrate. So I'm going to write that reaction over here. The overall reaction would be to react an aldehyde or a ketone with H2O, with H plus, and you're going to make a hydrate. Everybody kind of with me? So where does this equilibrium lie? Does it lie to the left or does it lie to the right? For most run-of-the-mill molecules, this equilibrium is going to lie to the left. In other words, you're not going to get much hydrate. But if we want to think, but let's think about this. How do I push the equilibrium to the right? I could use I could think about using Le Chatelier's principle, but the problem there is that basically the water's a solvent. So adding more water isn't really going to make that big of a difference. And of course, adding more compound doesn't change the equilibrium. Take away what?
But you want it to go towards the right?
That's what I'd like.
So you take away hydrate?
Take away hydrate, but the hydrate's the product.
Yeah, so then
I could do that. It's going to be really difficult. There's other cases where you could like raise the temperature and this hydrate would like boil out a solution, but this isn't one of them. So I'm kind of stuck here. I can't really use concentration, I can't use temperature in order to push the equilibrium to the right. But we're still going to figure out how to do this. We're not going to say, oh, sorry, can't do it. In order for us to think about another way, we need to review that equilibrium. And what's that equilibrium? So an acid becomes an acid, right? Dissociates to form H plus or H3O plus. How do I push that equilibrium to the right?
Might be able to add.
Nope. Nope. No, we're adding nothing. Can't take away stuff. There's 3 molecules. Which one of those is the strongest acid? Top, middle, bottom. Oh, wait. I have a phone. Now, I don't have extra cards, so Okay, which compound do you think is the most acidic, A, B, or C? Strongest acid. You don't have a card?
No, I didn't.
You should always bring your cards to lab or to lecture. All right, let's see what I've got. I've got 14 answers. That doesn't seem right. Seems like there's more than 14 people here. Oh, plus 2 guests, so 16. I got 8 A's, 3 B's, and 5 C's. If you chose A, why? There's 8 of you, besides him. There's 8 of you. Why'd you choose A? I mean, how many times have I humiliated somebody for answering?
Can I say why I think they chose it?
What? No. Zach, he raised his hand.
It's the most stable conjugate base.
Has the most stable conjugate base. True. Why is that the most stable conjugate base? Because of resonance, because all the resonance structures it has. What about B? B's conjugate base has 2 resonance structures, but not nearly as many as the sulfonic acid. And then what about the RO minus? No resonance structures. So A is the most acidic, B is second most acidic, and C is the third most acidic. Because this is the most acidic because it has the most stable conjugate base. What does that do to the equilibrium over here? If I make the conjugate base more stable, what happens? How about the equilibrium just shifts to the right? And when the equilibrium shifts to the right, what happens? We get more H+. The more H+ we get, the stronger the species is as an acid. So, what's my point here? It's a good question. I think my point is that we can push the equilibrium by adjusting the stability of the product. Make the product more stable, shift it to the right. Make the product less stable, it's not going to shift as much. Well, I can't do anything with the product of this reaction because now I got to go back and say exactly what were we talking about? We were talking about this equilibrium. So how do I force the equilibrium to the right? Well, I can't change really the energy of the product, but I could change the energy of the reactant. And how should I change? If I want to push this equilibrium to the right, what should I do to the aldehyde? Make it more or less stable? Hold on. Card. I want to push this to the right. Make the aldehyde more stable or less stable. And a couple things when you're holding them up, make sure your hand isn't covering the square, or it won't. There. Okay, we have 6 more stables and 11 less stables. So if I make the reactant more stable, how does the equilibrium shift? It usually shifts towards a more stable species. I want to make the reactant less stable. So if I can make the reactant, if I can make the aldehyde less stable, I can push the equilibrium towards the hydrate. Next question. Which of those two is more stable? A or B? More stable, A or B? Four for the aldehyde and 13 for the ketone. So your answer is that the ketone's more stable. Why? Amelia?
The more constituents, the more stable.
So the CO double bond is like a CC double bond. How do we make a carbon-carbon double bond more stable? Make it more substituted, give it more substituents. So ketones are no different. So which of these two compounds is most likely to form a hydrate? The aldehyde or the ketone? The aldehyde, because it's less stable. So this one is less stable, which is what we're looking for. All right, so I want to make an aldehyde that is like the most unstable aldehyde you can make. What should I attach? Well, I know I got 1H. What should I attach to the other side? I want to make this the most unstable it can be. What? That would make it a carboxylic acid instead of an aldehyde. What if I put an H here? And what is that? That's formaldehyde. So if you take formaldehyde and you react it in water, formaldehyde, just so you know, formaldehyde in its purest form, it's got two forms. It's a gas. It also can be a solid if it's reacted together with itself, called paraformaldehyde. But for the most part, formaldehyde's gas. If you react with water, you make a hydrate called formalin. Nope. Formaldehyde's so unstable it doesn't need an acid catalyst. So if you drop in water, bubble it in water, you're going to make formalin. Now, formalin has been used when you have dead things in formaldehyde. You really don't have them in formaldehyde. You have them in formalin. That keeps the dead things from decomposing. Except I think in biology they probably use methanol. Because I think they switched all the formalins when we moved over to this building a long time ago. So that's the aldehyde that we can make unstable. If I want to make a ketone, or I can do this by not using formaldehyde, another way to make this unstable is to add 3 halogens to the carbon next to the carbonyl. What happens there? The chlorines all pull electron density away from that carbon, which then pulls electron density away from the carbonyl. And this is called chloral. And if you react chloral with water, you will get what's called chloral hydrate. So two ways to push the equilibrium towards the right for a hydrate. Both of them make the reactant more unstable, and then that will push the equilibrium. How do you do that? Use formaldehyde or attach a halogen to the carbon next to the carbonyl. Okay. So that's how we make hydrates. So I can do this reaction with an alcohol as well. It's going to be the same boring mechanism. ROH plus aldehyde. We'll put a prime on that R. In the presence of an acid catalyst. So what should I do? First, protonate the oxygen. I'm going to use the intermediate with the plus charge on the carbon. Next step, add the alcohol to the C+, just like you would do any SN1 mechanism, except this is an SN1. And I'm going to add that alcohol, and so I'm going to end up with a plus charge on the oxygen. Next step, I'm lost.
The oxygen plus charge, you're going to add or take away the H.
Okay, I'm going to lose the H plus off the oxonium ion so that it'll become neutral. And then it will be somewhat happy. And so then I get this species, which is a hydrate, except it's not two OHs, it's an OH and an OR. So this is called a hemi, and it depends on whether it came from the acetal or the ketone, or whether it came from the aldehyde or the ketone. So this one came from the aldehyde because there's an R and an H here. So this is called a hemiacetal. If this molecule would have originally come from a ketone, there'd be two R groups there, and it would be called a hemiketal. But the problem here is this is only, what does hemi mean? All right, well, what is a hemisphere then? It's what? It's half. A hemi is half. So half of what? Well, half of an acetal or a ketal. So what do they look like? So we have to continue on. All right, so let's continue on. H plus, what's the H plus going to do? Which one? The what? Could protonate both of them, or either. What happens if it protonates the OR? System goes backwards. What happens if we protonate the OH? We'll move forward. But this system is in equilibrium. Okay, so now I have that molecule. I protonated the OH. What happens next? Hold on. Give somebody else a chance to answer. I'm reading all this stuff on how people are reluctant to answer, and apparently that starts in middle school. And there's a gender bias to it, because there's this girl that just wrote a book on
Claudia Lenhard.
On how to be brave and raise your hand. Everybody should be brave and raise their hand, except when I called on them. So what was my question? Oh, what happens next? Water leaves. And I've read the student evaluations from last fall or from last spring where don't randomly call on people. It's too stressful. Right. Okay, what's my last step here? What I'd like to do is I'd like to react this with another mole of alcohol. So actually up here there should be 2 moles of alcohol. And what's going to happen? Same stuff that always happens. Alcohol adds to the carbocation, forming an oxonium ion, and we lose our H plus to give us that, which is a full-blown acetal because it came from an aldehyde. And we'll talk about how you tell the differences between all these different molecules in the coming days. So this is the mechanism for forming an acetal from the reaction of an alcohol, 2 equivalents of an alcohol, and an aldehyde. If I asked you how to write the mechanism here for a ketone, you would just erase all the H's of the aldehydes and put in R groups, and they're all ketones. Okay. So one of the things that I would add to this sort of mechanism is I don't necessarily have to add the same OR group. I could stop at the hemiacetal and then switch. So if I only use one equivalent of one alcohol, like methanol, I could switch at the hemiacetal and add ethanol in the second batch. So they don't have to be the same, although for the most part, they are.
Based on, if you were to add just the one equivalent of the acid catalyst, for instance, to try and kick off the reaction, will it only make it so far down the chain? Or will it just stop at the one conversion and it won't move past the...
So you want 1 mole of acid catalyst?
Yeah.
Okay.
Instead, you have extra reagents, both of the two major reagents. So
Well, I have to have one in excess of the other. So I've got this in excess. The key part of your question is, what would happen if I just used 1 mole of acid catalyst? Would that affect? If I use 1 mole, 2 moles, 3 moles, would I get different results? No braveness. The key word is catalyst.
This will,
If I add more catalyst,
no, if you decrease the amount.
if I decrease the amount of catalyst, it'll go slower. Maybe. I mean, it's a rate thing. But the key thing is it's catalyst. So you're right, it may go slower. But how about the position of the equilibrium? That plays no role in the equilibrium. No matter how much you use, the equilibrium is going to be the same. So when you use a catalyst, it doesn't matter how much you add. Kinetically, yes. Thermodynamically, in terms of equilibrium problems, no. Last thing. So where does the equilibrium in this reaction lie? It lies to the left. What can I do to push it to the right? Well, we'll have to learn about that on Wednesday. Because if I make this acetal or ketal cyclic, equilibrium goes all the way to the right. And that's going to be a slightly different, it's going to be the same mechanism, it's just I'm going to make rings. Okay? So that's what we are going to talk about on Wednesday. So there's no assignments due for Wednesday, but I will get you some, and then also the clock will start ticking on the next chapter's top hat problems. Yes. Exactly.
Oh, I can work on it. Okay, cool. I'll just